is a coal seam gas region in the Strat Basin, Queensland. So measuring and understanding the different sources of methane gas, which you can get in gas bores overlying or near production reservoirs, is a bit of a ubiquitous international problem. So, for example, there's been some work in US shale gas reservoirs, but in those cases they're looking at thermogenic gas versus overlying biogenic gas, where you might have questions around whether the gas has been produced in situ or migrated or leaked. So in our case we're looking at coal seam gas that's been produced from the Walloon coal seams in the Strat Basin, and some previous work has shown that this is biogenic gas, which is generally of secondary microbial origin. It's a bit of a complex issue, but there's various overlying aquifers from the Great Artesian Basin and also the Condamine Alluvium, and these have various users in agriculture, feedlots, and of course in Australia we have had some droughts and issues. And so there's been recent and historic gas shows in some of these bores where they're getting dry. And one of the questions is, can we differentiate sources of methane or identify inter-aquifer connectivity or non-connectivity? So these are some of the overlying aquifers, and to the east side of the basin, the Condamine Alluvium overlies the Walloons, where the Walloon starts to subcrop. And also isoflasks, which is a closed method. We also sampled waters for various parameters, ions and different isotopes of waters, dissolved gases and dissolved inorganic carbon. In some cases we had some isotopes below detection, and we also analysed the total methane concentrations and C2 to C4 and some other isotopes that we're not going to discuss here. So here we're showing the dissolved gas concentrations from the isoflasks and the direct fill vials. So in yellow we could see for the isoflasks, and in blue and grey for the vials, where we had different sets. On the left we've got the results for the Roma region, and we get a reasonable agreement up to around 10 ppm, but above this the majority of concentrations measured by the isoflasks are much greater than from the vials. And also on the right you can see the Dalby and Chinchilla region, where we've got the coal seam gas production waters and the water bores, and again similar story there. So the Springbok sample from a gassy bore had the highest methane concentrations in the isoflasks, for example. So these results suggest that we're losing gas to atmosphere when we're sampling with vials, and underestimating dissolved methane concentrations when we're dealing with gassy bores. This is showing for the Roma region the water bore samples. So the coal seam gas is in the secondary microbial region, where we're looking at plots of delta 13C versus delta 2H, and also 13C of CO2 versus 13C of methane. Compared to this, where we're taking samples from the Gubberamunda, Orallo, Mooga bores, they're plotting in the primary microbial and fermentation regions, so we can see a good separation of the signatures there, and they indicate that it looks like we're getting in situ formation of methane. We also had one Gubberamunda and a Springbok sample that overlapped the coal seam gas samples. However, some of these bores also contain coal, so it's hard in these cases to tell if the methane is coming from in situ or from potentially migration. Chinchilla water bore samples and also the coal seam gas wells that we sampled, which are shown here. So the coal seam gas samples are again in the secondary microbial region with positive 13C of CO2. And then water bores are generally in the primary microbial or fermentation region. There are also some other samples which aren't shown in these two plots because we just weren't able to measure both of the isotopes to plot them. For example, there was 4 other Condamine bores where we got negative 13C of CO2 values. So unlike the coal seam gas values, which are generally positive, so that also indicates a good separation and in situ production. For 13C of dissolved inorganic carbon, the production waters, which you can see in highlighted in green here, they're positive for 13C DIC values. That's quite consistent with previous work. And then the water bores, we can see a range of 13C DIC, mostly have a negative signatures consistent with recharge. The gassy Springbok, however, highlighted nearer the top in yellow, has quite a positive signature, 13C DIC, and it also has more depleted water isotopes, indicating some methanogenesis. And for a couple of the water bores lower down, highlighted in yellow and blue, the 13C DIC was positive, indicating some methanogenesis perhaps, or on the slightly negative side. This is showing for the water isotopes. For the coal seam gas waters and the gassy Springbok, they were more depleted. So the gassy Springbok had the most depleted value, that's pointed out at the bottom. And then these are likely recharged during older, colder climates or show influence of methanogenesis. And then circled up in blue, the Condamine Alluvium samples, for example, were more enriched. And these are shallower bores, so there's likely some recent recharge or influence from surface waters. But Walloons water bore was the most enriched sample, which you can see up in the top right hand side. We did direct field sampling for methane with the vials, which is a standard method for monitoring methane in water bores, and we compared that to the isoflask closed sampling method. It looks like we may be losing gas and underestimating dissolved gas concentrations using the vials, well, especially when we're looking at gassy bores. We found a measurable difference between the methane and the CO2 stable isotopic signatures of the coal seam gas, and the majority of our water bores, which are in aquifers overlying the coal seam gas areas, and also for the Condamine Alluvium, indicating that the majority may be in situ production of methane in those aquifers and alluvium. However, we had a couple of samples where we couldn't distinguish the signatures with just the stable isotopes, and we couldn't really tell whether that was in situ process or migration. So using a multi-isotope approach with water isotopes, 13C of DIC assisted us with the interpretations of the methane origins, and we're also using further analyses of sulfate isotopes and strontium isotopes cosmogenics to look for connectivity and disconnectivity to help us with some of these tricky bores. Out of scope of this study, it would be good to do more sampling on some of these contentious aquifers and also pre-baseline sampling in regions of the Stratton Basin. And these methods can be applied in other areas such as shale gas or carbon storage basins to give you a robust baseline and better understanding. I'd just like to acknowledge the following people for money and for help with also for help with sampling and with analysis.